All right. Hey everyone. So today we are doing 1.4 polynomial functions and rates of change. So polynomials, we should know the word poly means multiple. So it is a non-constant polynomial is a function with many terms in the following form. A(n) xn plus a(n) minus 1 x to the n minus 1, so on and so forth, all the way until we get to a0 x0, where n is a positive integer and a1 is a real number. So here's an example of a polynomial. We have p of x is equal to 3x to the fifth plus x to the fourth plus 7x plus 2. So notice how in the example, although they're very general with the terms, right? We have a, n, x, n. It's supposed to be in descending order, right? With 8n, x to the n being the largest term. That's what's called standard form. So in standard form, I can see my leading term, which is the first term in a standard polynomial in standard form. So using my previous example, I can say that the leading term is this entire thing. So 3x to the fifth. Or if I wanted to keep it more general, I would say it is a(n) x to the n. Okay, now the degree of a polynomial is going to be your largest function or whatever, or your largest exponent, excuse me. So in the general example, that would be the n. In my example, my polynomial is of the degree 5. Okay, and again, if I were keeping it general, it would just be n. Now a leading coefficient is the number that's next to the largest exponent, which in my example would be 3. I'm just going to call it the leading I'm not going to write it all over again, which is 3. In the general example, it would be a n. Okay. Now I have a local relative or relative extrema. You can see it either way. You might see it on the AP exam as local, or you might see it written as relative. The point is that it's going to be your maximum and minimums. So if polynomial switches from increasing to decreasing, there will be a local or relative maximum. So when I have that in a graph, the best one to do is a parabola. Those are the easiest ones to see. So I'm going from increasing to decreasing, and I would have my local maximum somewhere around there at the top. Okay. Now, when I have a polynomial that switches from increasing to from decreasing to increasing, that's when I will have the minimum. So that's going to look like the polynomial, the parabola that we're used to, and then my minimum will be at the bottom of the graph. Okay. Now, I can have an included endpoint of a polynomial with a restricted domain may also have a local extreme. What that basically is saying is if I had part of, oh, I didn't press the right button. If I had a part of a graph, let's say I had a point here, and it went something like that. If I had a section of a polynomial, I can also still have that maximum or minimum. It's not required that the polynomial be continuous. It can be a specific range, okay? Then we have the global absolute extrema. Of all the local maxima, the greatest is called the global or absolute maximum. And then I have, of all the local minima, the least is called the global or absolute minimum. So that's going to be when I have a function that's kind of a little bit crazy. Oh, yep, didn't even work that way. So if I have a function that looks a little bit wonky, okay, I have multiple maximums, right? This is a maximum here. Here's another maximum. This one right here is my global or my absolute. And the same thing for my minimums. Here's one minimum, here's another minimum, but this one is lower. So this is my global or absolute minimum. Okay, now here we have the example. Find the extrema and where they occur. If there are none, cross it off and write none. So let me change colors. The absolute min of blank when x equals what? So again, we're looking for absolute. That means the lowest of the low. So if I look here, the lowest of the low of my extrema, it's going to happen when the absolute min of 1, right, because that's my lowest point there, occurs when x equals -3. Then I have an absolute maximum. So in this case, I have two maximums, one right here, one over here. Oh, this was another minimum. I forgot that's another minimum, but it's not the absolute. I have here one maximum, two maximum. Again, the maximum is going to be the tallest one, which is going to be when it is a maximum of 3 when x equals 1. And then I'm going to have relative mins at x equals, so that's at x equals -3. Remember, relative are the local ones. So those are all the ones you can have. The absolute is the biggest one. So I would have at -3. And then I would also have at 2. And then I have a relative max or maxes at -4 and 1. Okay. Now, 2 zeros, 1 extrema. If you have 2 zeros of a polynomial, non-constant polynomial, then there must be at least one local extremum between the 2 zeros. So that makes kind of sense, right? If I had my graph and I had 2 points on it, what this is saying is that if I have 2 zeros on my polynomial, then there's either going to be a maximum or a minimum. Okay, I have even degrees, and then they have absolute extrema. So if the polynomial has an even degree, there's either an absolute minimum or maximum. A positive leading coefficient means you will have an absolute minimum, and a negative leading coefficient means you will have an absolute maximum. So basically, I'm going to go back to my parabolas, right? If I had a positive leading coefficient, that means my graph is going to concave up, meaning I'm going to have a minimum, right? If it concaves up, I have to have a minimum. Or if my graph is concave down with a negative leading coefficient, then it's going to be a maximum, okay? Then I have points of inflection. So we've already talked about points of inflection, but this is a bit more of a elaborate definition. A point of inflection occurs at input values where the rate of change changes from increasing to decreasing, or vice versa, and occurs when going from concave up to down, or vice versa. So the point of inflection, what we're really looking at is when that rate of change is going to change, when that slope is going to change, okay? Because that's going to be the point. That's why when we looked at it on the graph, the points of inflection were not at the peak or the valley of the graph. It was more in the middle between the two, okay? And that's why, because we're looking for that change, okay? And that is it for 1.4.